So my name is Doug Schmidt. I'm a professor of computer science at Vanderbilt University. But in this context, I'll be talking also about the work that I've been doing together with my colleagues at the Software Engineering Institute, or the SEI, at Carnegie Mellon University. And we'll be talking about a study that we've been doing to think about what's next for software engineering and how we can better work together to architect systems of the future. So without further ado, let's go ahead and start. I'll give a quick summary of what I'll be covering today, and then I'll get into the contents. So I think it's pretty clear that we're all more and more reliant on software. You need no more proof of that, but to look at the news every day when something goes wrong, there's a software breach or an attack or something fails, and it's imperative to address these types of concerns that we continue to innovate the theories, the tools, the practices, the methods, and so on that we use to develop software. We also need to figure out how to assure software continuously and be able to insert new capabilities as quickly as possible. And that'll be a theme that I'll come back to a number of times in this talk. It's relatively straightforward nowadays to put systems to field quickly. It's hard, but not impossible, to assure that systems work correctly, but getting systems to the field quickly that are assured is very hard. In order to solve these kinds of issues, we're going to have to think about new ways of doing things, and in particular, new research. And again, this is very highly motivated by the need to get rapid deployment of assured capabilities. And that's going to take more than just what we have today as status quo in terms of tools and languages and platforms and so on. So in order to address this, the Software Engineering Institute at CMU has recently led a study to evaluate and reevaluate and redefine how software should be developed. And the idea behind this study is to help catalyze the community, obviously the research community, but also indirectly over time, the practitioner community as well, to come up with a multi-year R&D vision, strategy, and roadmap to engineer these next generation software reliant systems. And this document, which will be the focus of my talk today, is going to be released hopefully next month. So this is the cover art for it, so you can see it's coming along, and we're going through the final rounds of edits and approvals and so on to get it released. So it should be available publicly from the SEI website here soon. So what is the purpose of this? Well, again, just to underscore the point I made before, software is absolutely essential to be competitive in today's global economy, to be secure in today's global economy. Every time you turn around, there's another ransomware attack or another cyber breach that leads to enormous loss of money, loss of capability, loss of reputation. And therefore, it's pretty clear that global economies, infrastructure, education, entertainment, healthcare, and so many more things all depend heavily on software. So if we want to improve quality and productivity of software, we need to figure out what the new challenges are, and I'll be spending a bit of time on that when we try to engineer these software-reliant systems. It would be helpful, especially if you're in the research business, like many of us are as academics and people who work in R&D labs, to have a roadmap that can help decision makers and sponsors decide where to put their investments to provide new and better foundational software engineering principles across the range of new system types like intelligent and autonomous systems, safety critical systems, data-intensive systems for machine learning, and so on. Something else that's also important for those of us who work in this particular field is making sure that the folks who make the decisions about allocating resources understand how important software is, and it gets sustained recognition. Sometimes there's this somewhat misplaced belief that if you leave industry alone, they'll solve all the hard problems in software. And industry certainly has a very important role to play in software, but oftentimes their focus is much more short-term, and their focus is much more on the bottom line for their particular company, their particular group or consortium. So we need to think more broadly about how we can drive innovation across the board. And something else that's important that I want to underscore throughout the talk is the need to get partnerships and collaborations that will bring together industry practitioners and research labs, academics, and of course, governments that provide lots of funding in many cases for this type of work. So let's start by talking about some of the new types of systems that are going to require advances in software research and development. So one type of system we see increasingly are the need for highly adaptive mission-critical and safety-critical systems. A good example might be space exploration, where where you don't know necessarily when you launch your space vehicle all the different environments it will encounter. So the need for adaptation and some autonomy locally is important because it's not always possible to phone home to the mothership to get direction. Other good examples of new types of systems are systems that have to perform data fusion at huge scale. Think about trying to do climate change analysis or even something as mundane as weather prediction. I'm currently in Florida in the United States, and I was supposed to be here on Tuesday night, but there was a hurricane that was scheduled to come in. Well, it turned out that the hurricane actually wasn't very disruptive, but that didn't prevent my flight from being canceled, so I had to come a day later. So being able to fuse large amounts of data would make it possible to predict those kinds of weather events more accurately, thereby saving lots of money and time and inconvenience. Obviously, highly available business enterprises. Almost every business now relies on software. Witness recent ransomware attacks that took down pipelines and food ecosystems, food supply chains, at least in the United States, if not around the world, making it clear how people depend on IT to do their business. Something else that would be nice would be personal digital assistants that actually help and do things more than just give you calendar alerts when a meeting is coming up. Something that really looked into the way you're using the technology, the types of meetings you have, provide you with information about upcoming meetings that you might want to read about or papers that would help you prepare for a keynote talk would be helpful. Something else, of course, that's very important because of the dramatic cost and impact on global society is holistic healthcare and personalized healthcare. And taking advantage of our reliance on mobile devices that can sense many things about our mood and our movements and our engagements with others. These are things that can be fed in a very fine-grained, continuous way into more expensive and less frequent types of analyses, things like an MRI or a CT, trying to figure out ways to combine low fidelity but high frequency actions with high fidelity, low frequency interactions and doing a better job of helping people with their health and their mental wellness, especially in today's pandemic isolated world. And then, of course, something else that's probably near and dear to most people's hearts, especially these days in our move towards energy efficiency and sustainment, are smart cities, buildings, cars, and so on that will do better if we get more information to them at the right time. There's also a number of trends that are motivating changes to support these kinds of systems. Obviously, systems are getting bigger, and very few people have the luxury of building these systems from scratch with components that are all done in a bespoke and custom way. So we need to find a way to be able to build safe and resilient systems by composing existing pieces, some of which have varying degrees of pedigree that we may not always be sure of. We'd also like to be able to, as I mentioned before, be able to deploy software rapidly and continuously in an assured manner. That's a trend that we see more and more, especially as we get more dependent on software. Something that's a big problem, certainly in the US, if not around the rest of the world, are being able to address gaps in software talent. Software talent is not distributed equally. There's some groups that have a lot of experience with it. There are other groups that don't. We need to try to find a way to bring many different groups up and help make it more equitable and diverse because we need everybody working together on these hard problems. Something else that you see is a very common trend these days, especially in the research community and beyond, is looking for ways to have artificially intelligent automation, trying to use technology at our disposal to make things work better without having people have to be in quite so many parts of the overall loop. When you start doing those kinds of things, of course, and then it becomes important to make sure that what you build is something you have confidence in. So coming up with new ways to provide evidence to assure that systems work as intended and don't do things they're not supposed to do. That's a very important trend, especially as we're getting more ingrained in mission and safety critical domains. Something else that we're going to talk a bit more about later is the fact that we're starting to have our technical platforms, like our social media platforms, much more engaged with people. And it's a multi-phase, multi-dimensional event loop, if you will, where people have input into the system and people's behaviors are also guided and driven by the information that they receive, which is increasingly tailored for their particular idiosyncrasies and desires and hopes and fears and so on. And this is having a very large impact on society and as a whole. And then something else that I would be remiss if I didn't mention is how important data has become. When we think about software engineering, historically, we thought about writing code. But increasingly, as we're working with data-intensive styles of analyses, data science, machine learning, and so on, the primacy of the data is important, and making sure the data is accurate, making sure the data is clean, making sure the data is as free from bias as possible is very important if we want these systems to actually deliver on their promise and not lead us down the primrose path to something we're not really going to enjoy the outcome of. So our study has been something we've been working on for the past couple of years. The way we did this is we have an advisory board that has some leading thinkers, people like Vint Cerf and Bill Shirless and other people that you've undoubtedly heard of before who are very well established in the software research and development community. We obviously went out and surveyed the computing landscape, looked at emerging technologies, reviewed a lot of literature, interviewed a lot of experts, conducted a number of workshops, and then did a little bit of brainstorming to think about what might be coming down the path, depending on which way we see the future going. And the goal here was to cast a wide net that could include input from many different diverse communities. This has led to our research agenda study, which is a roadmap and a set of recommendations. As I mentioned, that should be available soon. So the goal of this, of course, is to not just have another roadmap that gets in an ever increasing height of stacks of things that people don't read, but try to codify our findings in a way that are actionable by the decision makers. And then hopefully we can unleash this into the world at large and the ecosystem, which are the people out there who are producers and consumers of software technologies and software engineering methods, theories, and tools, and so on, will be able to act on the findings in a useful way, hopefully. And that's always a bit of a gamble because you never quite know where these things will go. So let's start by giving a brief summary of the vision we came up with for the future of software engineering. And this is probably not going to be a big surprise for people, but the basic idea here is that rather than doing what we do today, where we throw a lot of people at trying to do the various phases in the software lifecycle, requirements analysis, specifications, high-level design, architecture, detailed design, implementation, testing, and so on and so forth. Try to come up with a way where we move away from a very intensive, people-centric way of doing things to one where that software pipeline for the lifecycle consists of people plus AI that can work together in trustworthy ways to collaborate to more rapidly evolve systems based on ferreting out what the users are trying to do. Now, there's good and bad things about this, and you can imagine we'll talk about some of the good and bad things as we go along here. But if we just suspend disbelief for a moment, to accomplish this vision is really going to require advances in two main areas: development paradigms and architectural paradigms. So I'm going to briefly talk about each of these different themes, and then we'll go into more detail. So development paradigms, of course, involve things like languages and platforms and interactive development environments and methods and tools and so on, designed to increase the efficiency and trust of the resulting software as we scale up. And we've identified three main development paradigms we're going to cover in more detail. The first, which is sort of underscored by the vision, is we want humans to be able to leverage AI, and I'm using that loosely because it doesn't have to be something that's necessarily based on machine learning, but it can be other forms of automation and keeping track of things and knowing what your intent is. And think about the modern interactive development environments you work on today that can do an awful lot of things behind the scenes for you. Things like the Spring framework, for example, the Spring platform. And the goal of this, of course, is to be a workforce multiplier so that we don't have to have as many people doing the work and we can rely more on automation to help us out to create and sustain software. So that's one theme, but we'll talk more about that in a second. Part and parcel of this, although also unrelated because there's lots of things that are not AI-based that also require what I'm about to say, are ways of being able to have formal assurance arguments that can evolve to assure and efficiently reassure software as it evolves continuously. And this is one of the big challenges we have today when we talk about mission and safety critical systems. It takes an enormous amount of time and effort to assure these systems. These would be systems for defense or space or air traffic management, things like supervisory control and data acquisition systems that control power grids and so on. Making sure these systems do no harm is very time consuming and very expensive. And yet we have to evolve these systems. And so trying to come up with new ways to provide some higher levels of confidence that we can evolve these systems at scale is very important. And then speaking of doing things at scale, as I mentioned before, we aren't going to build all these systems from scratch. So we're going to have to take a bunch of components some of which were developed to be used together, some of which were developed in isolation when were not designed to be used together. And we have to find a way to be able to predictably construct these large systems and make sure that we can do this in a way that will be amenable to regulations and policies and certification requirements that we increasingly have. So those are some of the things I'll talk about in more detail in a second, just giving you a bird's eye view. Then there's also, of course, emerging architectural paradigms that will enable the use of new computational models. Some of these will be perhaps familiar to you, others may be less familiar, but I'll just go through them quickly. So one of the things that's happening these days is we have increasingly large sociotechnical systems that have global scale. Good examples of this, of course, would be things like social media platforms like Facebook or Twitter or TikTok or YouTube, or pick your favorite social media platform that you probably spend more time than you should sharing more than you ought to lots of people around the world, some of whom are your friends, some of whom are not. And trying to figure out how we can program, I'm using that word loosely, these kinds of large-scale, sort of societal-scale systems to yield more predictable outcomes that are less prone to bias or less prone to emotional overreaction when misinformation seeps into these systems and percolates rapidly through the network, much like the coronavirus did. We'd like to be able to come up with a new way to be able to make those systems work effectively without having all the side effects and downsides we have now. Another topic that's important, although I think to some extent it's still a bit of a pipe dream, is to come up with new ways to develop quantum-enabled systems. So you're undoubtedly aware that there's a lot of emphasis all around the world from many different research organizations, many different governments on so-called quantum computing. And quantum computing has a tremendous potential to do radical new things that will change the way that we think about computation and can solve what today are intractable problems very rapidly. However, people haven't thought a whole lot about how do you program these systems. They're thinking primarily about how do you build them from a hardware architecture point of view and sort of a probabilistic computing point of view. But how do we program these systems? How do we take advantage of them? And so on and so forth, and not let them mislead us in various ways. And then, of course, the other architectural paradigm that needs to be thought through is how are we going to engineer intelligent systems so they have all the degrees of confidence and reliability that we've come to expect from our existing mission and safety critical systems. So as we'll see, this is kind of the flip side of using AI to build software more effectively. This is using software engineering techniques to try to rein in what potentially could be a very problematic, open-ended artificial intelligence style system that would lead to all the kinds of things you watch in dystopian movies like Terminator 2 and war games and other things where computers take over and run the world and destroy everything. So we'd like to figure out a way that we can have these newer computational substrates that are going to still work within the bounds of civilization and ethics and so on. So this was the starting point. These were the areas we came up with as a result of quite a long bit of deliberation and discussion and debate and interaction with experts and our advisory board. And so we took a stab at defining a software engineering roadmap for research focus areas and research objectives. And the goal, of course, is to think over the next 10 to 15 years. Again, there are two paradigms, the development paradigms and the architectural paradigms. And the goal of all this stuff is the vision of this is to have humans and to have AI work together as trusted collaborators to more rapidly evolve systems in a robust and secure way based on the intent of the users to the extent that we can ferret out that intent. So these are the 6 different research topic areas that we came up with. I will go through them in more detail, so I won't go through them in detail now. I'll just mention them. So it's AI augmented software development, assuring continuously evolving systems, software construction through composition. Those are examples of new and emerging development paradigms that we think are necessary to help provide the foundation for the future of software engineering and software-reliant systems. And then from the architectural side, we have engineering societal scale software systems, engineering AI-enabled software systems or engineering of intelligent systems, and then engineering quantum computing software systems. I'm going to talk about the first 4 topics. I'm going to leave the other ones off in the interest of time, but they are also absolutely fascinating topics. When the report comes out here in a month or so, you'll see that we have a roadmap with sort of milestones and objectives that we hope could be achieved over the next decade or so. I will not go through those in excruciating detail in this talk to keep it at the right level, but be aware when the report comes out, you can find out lots more about the thinking that goes behind this than I'll have a chance to present here in a short time together. So let's start off first by just re-summarizing those development paradigms we see as crucial for the future of software engineering. The first one is the AI augmented software development research area. And the focus of this is to figure out what types of artificially intelligent augmented software development techniques, tools, platforms, environments, and so on could be created. How do they get fit into the overall software lifecycle? And how can they be used to make software programmers, people like you and me, more productive in building higher quality code more rapidly and fielding it? And obviously, the starting point for this is to try to automate as many of the mundane, routine tasks as possible to make the system be more effective at leveraging all the advances in hardware and software like Moore's Law. In other words, being able to use automation to more intelligently steer things like quality assurance. There obviously are moves in this direction already, and I'll touch on them when we go into this in more detail in a second. The next research area is assuring continuously evolving systems. And the idea here is to develop a theory and a practice for being able to rapidly field assured software for systems that are continually changing. Some systems don't change very much. In particular, classic things like safety critical embedded systems, like the braking system, the anti-lock braking system that you would have on your car, for example. Those things don't change very much. Once they're deployed to the car, they rarely, if ever, change. But more and more, we need to be able to update these systems, if for no other reason that there are often unexpected vulnerabilities or safety hazards, and we'd like to find a way to update things safely and securely so that we can take advantage of new advances and bug fixes, if nothing else, and security patches. And how do you do that in a way where you can field new capability without having to spend months or years recertifying it all? That's a huge challenge, and I'll talk a bit about some ways to go about looking at that. The next topic is one that's very near and dear to my heart. I've spent most of my career working on middleware technologies and tools for composing applications out of pieces of software. And so the idea of reuse and the idea of multi-use software components is crucial to what I find interesting. And what we really need to do is think about this in a new way, because we want to be able to build these large systems, and we want to be able to leverage newer design and development paradigms, things like model-driven engineering, things like annotation-based dependency injection frameworks, which give us new ways of composing software by either generating it or wiring it together. And yet, if you take a look at the technologies and tools that exist today, they're still somewhat limited. And I'll talk a bit more about that in a second. Again, just to recap the architecture paradigms: engineering, societal scale, software systems, which is basically looking at ways of coming up with programming social networks so we have better outcomes than the type of misinformation and propaganda that we're often exposed to today. Engineering AI-enabled software systems. How can we find ways to deal with the fact that AI systems, almost by definition, have outputs that are often not known in advance? So how can we build the appropriate testing and verification techniques and tools to try to make sure that those systems stay within the guide rails, even though they're not always producing the same results every run? We want to make sure that what they're getting back makes sense, is trustworthy, isn't biased, and so on. And I think that's one of the crucial challenges for people's excitement with the use of AI and things like, for example, driverless cars or airplanes or anything that automates loops where humans used to be central to that. We're trying to replace humans. And we have to think very carefully about how these systems aren't going to jump out of the box and cause all kinds of problems that we didn't anticipate through their emergent behavior that will have bad side effects. And then the last area, which I won't go on to in much detail anymore, is engineering quantum computing systems. And the whole point here is people have been focusing so much on the hardware. Now it's time to start thinking about the software aspects and how do we program these systems? How do we verify these systems? How do we optimize these systems? And I think we're really, really in the infancy of those areas. So assuming we can ever get to the point where we have quantum computing hardware and platforms to play with, The big questions are going to be, what kind of compilers are needed? What kinds of optimizations will be useful? What kind of programming languages will we use? And those answers may not look very much like what we're accustomed to today, because we've optimized for common architectures that get more transistors and more cores over time, but still look quite a bit similar to the way we've programmed over the past several decades. So what I'm going to do in my remaining time is kind of go into some of these areas in a bit more detail, and then we'll leave plenty of time for questions at the end. So the first area to kind of do a deep dive on is AI augmented software development. And the idea here, of course, is to leverage all the advances that have happened over the past, say, half decade or so in deep learning and machine learning and transformer-based approaches, search-based algorithms, in order to build tools that we can use as software professionals to be more effective and more productive at producing what we need to produce. So we need to figure out which stages of the software lifecycle are amenable to AI augmentation. My starting point is typically the quality assurance aspect, because I think that's where we have a lot of bang for the buck. Having more intelligent regression testing environments that don't have to rerun all the tests when something changes would be fantastic. There are things like that already, but we can do more. Being able to think about what people do versus what computers do, and striking the right balance is important. Computers are really good at doing mundane tasks that people get bored with, but they don't really necessarily, at least not yet, have all the creativity that we'd expect a person to have to be able to see connections that may be sort of lateral thinking that doesn't work in a linear way. Computers may be harder pressed to do that in any sensible manner. And another key thing is, how do we get to the point where we can more effectively express our intent to computers from the point of view of software development? You're probably already seeing the proliferation of chatbots and the proliferation of answering machines or answering services that direct you through menus that are voice driven, and you can say things and they'll try to figure out what you intend. But we haven't really gotten to the point where we can do that with software development, which of course is much more precise, and phrases and expressions and statements mean something very specific, and we don't want them to be misconstrued because you're unlikely to get the right result. So here are some of the open research challenges for AI augmented software development that appear in the report. Basically rethinking the software development lifecycle in an AI augmented way. What does that mean? How do we get user intent to build software? People are often very imprecise when they speak to each other about software, unless they're well versed in things like software patterns, where you can be fairly precise when you express yourself to your colleagues and yet still leave enough wiggle room to do appropriate implementations and optimizations. When we write code, we have to be very precise, but we don't speak quite the way we write code typically, unless you talk to software engineers and they speak in Java or JavaScript nomenclature, which would be rather odd, I'm sure. Figuring out what kind of data is needed to model each stage or workflow in this approach. Where will that data be collected? What format will that data be in? How will we protect it? How will we ensure that it's reliable? Figuring out how humans and computers can work together so that AI is actually useful and not just an impediment that keeps second guessing us or making changes that we don't intend. Something else that I think, again, is probably the secret sauce for initial progress here is determining how to keep track of evidence necessary to provide higher confidence that the software system will behave as intended. That, of course, requires capturing user intent. And then using AI to generate all this metadata and other information that is very tedious to do manually, but could potentially be handled more effectively through intelligent automation. And then, as we'll see in the next discussion, figuring out how we can use machine learning and deep learning techniques to help orchestrate the continual evolution of our software, which is a good segue into the next topic, which is assuring continuously evolving systems. These types of systems today, when I refer to continuously evolving systems, obviously all systems, unless they're total dead legacy systems, will evolve. But I'm thinking here primarily of mission critical and safety critical systems, things like SCADA systems that control power grids, things like systems that control medical devices, medical instruments, systems that control the air traffic management system, systems that control defense systems or homeland security style systems. All these systems need to evolve, and they need to evolve because user needs evolve, requirements change, new threats emerge, new opportunities for business emerge with things like the industrial internet and so on. And you have to think in these kinds of systems of evolution as being both functional, adding new capabilities to meet new functional requirements, as well as the so-called non-functional or quality attributes, characteristics like latency or jitter or survivability, resilience, reusability, modularity, etc. And there really need to be advances in two primary areas for this type of research to get us to where we need to be. And one of those areas is theory of evidence, and the other is theory of evolution. So theory of evidence really means combining different types of evidence, where evidence would be things like results from various kinds of testing, penetration testing, various kinds of regression testing, other types of testing where you just throw lots of gobbledygook at a system and see what it does. Obviously, there's other forms of evidence as well. There's formal proofs, there's output from various tools, model checkers, and so on. And trying to find a way to keep track of all those different types of evidence and then being able to automatically create either formal or semi-formal arguments or so-called assurance cases is crucial to give people higher confidence that these systems do what you expect them to do. And this is a big deal. I do a lot of work at the SCI on systems that are very mission critical, things like flight control systems for various kinds of aircraft, things for larger command and control systems, and so on. And people are always starved for evidence that these systems are going to do what they want, especially when they start trying to use newer technologies and newer innovations, newer platforms, things like reactive microservices in multi-core platforms. That tends to drive the safety certification people nuts because they don't know how to assure those kinds of systems. They don't know the types of arguments that are going to demonstrate confidence and so on. The second aspect, which is important over the life cycle, is a theory of evolution, which basically says as the system inevitably changes to reflect new requirements and new environments and new threats and so on, how are we going to evolve it? What kinds of failure models might occur that we didn't anticipate with the original design? What kinds of vulnerabilities will occur? We're seeing more and more vulnerabilities all the time with things like the recent supply chain attacks with the Kaseya ecosystem, where the actual patches that were meant to be pushed automatically to fix systems and fix bugs were actually carrying the viruses. Boy, talk about a problem. So how do we evolve these systems? How do we automatically generate and analyze data collected at runtime as unobtrusively as possible? Because a lot of these systems are time critical and they can't afford to miss deadlines. How can we get automatic suggestions to improve the system's state and the system qualities? How can we combine human expressions of what we need to be done with information that comes from the computer? This goes back to the AI augmented development theme from the previous focus area. And then, of course, to what extent can we use intelligent techniques based on machine learning and other sort of data science-y like approaches to generate evolution trajectories, so you can do hypothetical analysis. If we change the system architecture in such and such a way, what will the implications be on latency? What will the implications be on reliability? What will the implications be on security, and so on and so forth? And right now we just don't have tools to do that, so not surprisingly these systems take forever to evolve and change. The next topic is software construction through compositional correctness. And this is basically what I mentioned before. How do we build systems out of components, not all of which were designed to work together originally, and compose them together such that the whole is more robust than the component parts in isolation? We have some examples of this in the past. Things like the Internet Protocol Suite. TCP/IP is a great example of an end-to-end approach to providing reliability that is intentionally designed to be more robust than any of the individual pieces. Individual routers can fail, individual queues can fill up, but the TCP protocol and the internet can be designed to route around isolated failures. So taking that kind of as a metaphor and then expanding it to higher layers in the stack is really what this is about. If we want to be successful with doing this, we're going to have to think about new ways of composing software, perhaps using model-based approaches, perhaps using these annotation-based dependency injection style frameworks. And the goal here is to be able to add the pieces incrementally, add updates to implementations of the pieces without having to go through and reassure and recertify an entire system. So ideally, you'd like to bound the amount of effort needed to do this type of certification. And in particular, what we'd really like to do is we'd like to make the certification and recertification and assurance costs, both in time and effort, grow no more than linearly with the size of the system and the scope of the change. That isn't the way things work today. When things change, it typically takes much longer to recertify everything, especially for mission and safety critical systems. So how can we do this? Well, there's obviously some things we can draw upon from the past. People have been looking at model-based approaches for decades. People have been looking at aspect-oriented approaches for decades. Those have gotten us part along the way, but we're still missing some key elements. A theory of composability that supports cross-cutting concerns and quality attributes. The cross-cutting concerns that things like aspect-oriented programming typically thought about were primarily functional, and they didn't think as much about some of the quality attributes like timing and survivability or resilience and so on. Another key theme here is to get experience with this and then document the patterns that work and the anti-patterns that don't work, and then codify those things in tools that can enable the specification and enforcement of composition rules. We're getting better in this regard, certainly from a tooling point of view. If you look at modern dependency injection frameworks like Spring with annotation-based approaches, you can compose together systems relatively quickly out of pieces that were designed to work in isolation through microservices and so on. But the problem is we don't have good techniques for assuring those systems, especially at design time. Right now, with those kinds of systems, you typically have to deploy them and test them using some type of continuous development, continuous integration style approaches to see if they work, which is not acceptable in a lot of mission and safety critical environments. So we have to have better integrated tool chains that can assure these behaviors at scale and earlier in the life cycle. And then another key thing is that different research communities look at different aspects of this problem. And so often real-time people will look at real-time aspects, and reliability people will look at reliability aspects, and safety people will look at safety aspects. But we haven't really figured out how to join all those communities together with respect to the integrated tool chains that are needed to end up with non-siloed approaches. So these are some of the key challenges that we're facing in this space, even though we've made a lot of progress over the past decade or so. The fourth and final area I'll go through here briefly in terms of important research, and this is more of an architectural paradigm than a development paradigm, is how do we engineer sociotechnical systems? We live in a world where we live with software. We depend on software. Software provides us with our news. Software provides us with our biases. Software reinforces our biases. Software shapes the way we see the world. And issues like ethics, bias, misinformation are all crucially important in this brave new world we live in that's a software-centric world. And things like social media platforms like TikTok and Twitter and Facebook and YouTube and so on are very crucial at defining and shaping human behavior. And we have to figure out a way to make these things work for us as opposed to work against us. And it doesn't take too long to go through the news over the past couple of years to see all kinds of ways that social media platforms are used as propaganda, as ways to increase business. Think about what happened with the GameStop incident, where prices of stock were going up and oscillating wildly because people were playing games with social media platforms. Think about cryptocurrencies as an example of that. Think about various other events that have happened over the past year where social media has been used for all kinds of strange and perhaps unintended ways. So what we'd really like to be able to do is figure out how to have these societal scale systems, because I think we're all somewhat wedded to them unless you want to live completely off the grid, while mitigating some of the ethical risks, things like privacy. Are you oversharing to the point where bad people can find out about you and steal your identity? Trying to tamp down on just reinforcing the echo chamber of bias, trying to give out trusted results that are not going to be filtered through a lens of one political perspective versus another. Try to make sure that it's more clear when something is in fact propaganda as opposed to being masqueraded as truth. And then trying to, prevent unrestrained social manipulation. These are really, really hard issues, but if we don't get a handle on them, I worry that we're going to tear ourselves apart as a global society. So what's needed here? Well, we need new approaches that combine other disciplines besides just computer science. We need people with expertise in economics, sociology, psychology, game theory, ethics, in a way to be able to develop our software that is more adaptable and more apt to be able to give you an accurate view of things that doesn't get filtered through as many biased lenses. And again, this is a very, very tricky issue because it fundamentally comes down to people and culture and different ways of looking at the world and politics. It would be nice if we had environments where we could experiment with societal scale systems without having to unleash them on the world. I'm sure you're all familiar with companies like Facebook and so on who've done various experiments, A/B testing. I think, not to single out Facebook, everybody does A/B testing with their customers these days to try to see what they're going to like and what they won't like. But it would be nice to be able to do this in a way where we can get accurate results without necessarily having all the harmful side effects or potential harmful side effects here. So we need to have new quality attributes, new architectures, new analysis tools that account for people in the loop, whereas historically we haven't thought about that as much. We need to think about a theory of sociotechnical epistemology, which is just a fancy way of saying, in our brave new world of social media platforms, what constitutes justified true belief? You can go back to Plato and Aristotle and other famous philosophers to talk about epistemology, but it really comes down to how do you know what you know and how do you know what you know is accurate? Tough issue. There's all kinds of trade-offs between different quality attributes, time to market versus conformance to regulations and policies. There's a big push these days, at least in the US, to try to regulate the influence of social media platforms. How successful that will be is another story, but that is something that we have to think about when we build these kinds of systems. And then another thing that we're doing with varying degrees of success, I'm not entirely sure we've done a very good job of this, is to try to automatically detect and protect against misuse of these platforms. And again, everybody has their own view of this stuff, but a lot of times things get labeled in various ways by social media platforms, and it's not always entirely clear that what they're doing in this is something that is actually based on accuracy versus just trying to serve interests that are paying them or regulating them to do what they do. So this is a big, tough issue. Of all the things we've talked about so far, I would say this is probably the hardest issue and the one that needs the most research, because most of us as technologists don't think enough about these things, but instead we're simply buffeted around by the winds of change and the vagaries and whims of people who run these platforms, and we don't have enough opportunity to make a difference. So just a couple last parting thoughts as I wrap up, and then we'll take some questions. It's kind of summarizing what we found in our study. So clearly, software engineering profoundly impacts everything we do. We rely on this for all aspects of our economy and our society, increasingly our entertainment, in a world where we don't often get as much chance to see people in person as we might like. There's a bunch of new issues that will influence the way in which software engineering has to evolve, and these include things like smart cities, smart automation, systems that try to do a better job of helping the user, personal digital assistants, so on and so forth. And we need to figure out how these technologies can work for us as opposed to against us. We don't want a situation where nobody knows how the systems work anymore, which is increasingly the case with complex computing systems. Nobody knows how they work, especially the ones that are using older technologies that are faced with a dwindling technology workforce because everybody's retiring. We need to think about how we can integrate heterogeneous systems and systems of systems out of pieces that were not designed to work together, because we want to be able to support these new kinds of software environments and software-reliant systems we talked about. Beyond just the technology stuff, which of course is probably what most of us like to spend our time thinking about, we have to think more broadly about how to address the social implications, privacy, trust, freedom from bias, transparency, accountability. These are issues that are very thorny because they're not easily solved by writing a program. They're solved by thinking and discussing as humans. This is not the kind of issue also that can be solved in isolation. We as technologists have to partner with, we as academic technologists have to partner with our friends in industry. We have to partner with our sponsors in government and governments. We need to think in many cases internationally, because a lot of these issues don't stop at a national border, as we're seeing with things like ransomware attacks and so on. They aren't confined to one geographic location. They can go anywhere. We also need to think about how software engineering impacts and is impacted by many other fields. It's also probably human nature to focus more and more on less and less. That's how you get a PhD, and that's how you become successful in academia. But a lot of these things take a broader view, and we can't solve them if we just work inside our silos. Something else that's really important here is that this is a worldwide activity. There are people all around the world who are participating. And so we have to be more effective at teaming. Fortunately, there's lots of technologies that are making this way easier than they were a year and a half ago. So we're doing this conference by Zoom. Zoom has been fantastic at being able to unleash people's ability to interact, things we didn't used to be able to do, like, for example, we now have a remote PhD program at Vanderbilt University. We never had that before. We have that because people learned to work remotely by necessity as a result of the pandemic, and now we're able to do things where we can work together by choice. And then the final point, and I'll switch over to questions if there are questions, we need to be more effective at training the current and next generation of software developers so that they are more facile and more capable of solving today and tomorrow's problems by using today's tools, and perhaps even more importantly, by developing new tools based on R&D so we can solve the hard problems of the future. So with that, I will end my discussion and turn it over to anybody who has questions.